act like it's working. Taking a long time to update my settings on YouTube. Okay, there we go. All right, so I can't see any. Normally, I use my website as a guide for what's going on. I was going to show you everything we're doing the rest of the year, except 2 years ago, because that was the last time we went through the end of the year. We've got electrostatics, which is why I'm going to be rubbing the rabbit on balloons today. Works way better than human hair. I'll come back to that. I'll be rubbing a rabbit on the balloon. And so this unit is, if you're at home, you got the one that I screwed up that says packet or unit 8 packet, but it should be unit 9 packet electrostatics. This is static electricity, so we're going to be charging things or learning about things that have a positive and negative charge, but not talking so much about moving electricity, which is the next unit, current and circuits. And then after that will be sound and waves. But instead of waiting for sound and waves, we may take a little break, either maybe the beginning of next week, maybe middle of next week. I don't know exactly when, but we'll stop and work on string instruments for a while. That way you'll have those, and we could be doing some stuff with them for the rest of the year. And if you need to cope with this year, you can just sit around and play your ukulele or whatever you need to do to get through. And so this unit, electrostatics, next unit is circuits and current. And then after that, we're going to do sound and waves. And then if we have time for it, optics. So sound and waves go together, but optics, light is also a wave. And that's just kind of like sound, except with the visual spectrum. What else do I need to tell you? Oh, well. I'm just going to start in. So the warm-up was about this. It's so funny watching myself. It's like I'm shooting around here. There's a lot of lag, and it seems like, I don't know why I can see it on my screen. I look like the Flash. All right, so here we go, rubbing the rabbit. If you want to play with the rabbit in a little while, you can do that. This is, I don't know the history behind this rabbit. I may have shared this. It used to live under our deck. I had my Cocker Spaniel scare it out one day, and I shot it. And then I made it into pizza.
That's so sad.
It was really good pizza. We make this Big Mac pizza. It's like everything that's on a Big Mac, except in this case it was rabbit instead of beef. Yeah. So anyway, once I've done this with the rabbit, you might be able to see this on the. Before I had these big long strands. See that? Some sort of thing I've made of rabbit fur, and people at home may be able to see that rabbit fur strand stretching out. You can see the rabbit tail or whatever part of the, yeah, that is the tail. That's the cotton tail right there, reaching out for the balloon. They're attracted to one another. And I've got so much fur on this balloon now, it kind of feels like it may not be working as well. If I let go of this, it sticks to me. It'll stick to the rabbit. Should stick to the screen. Whoop. Kind of rolls down the screen until it gets to this lip usually, and then it'll stay there. So can anybody explain how it does that? Just the basic principle. Rub a rabbit on a balloon. Works well with cats too. If you have a cat, rub a balloon on it, and the balloon will just stick to the cat. You don't even have to shoot the cat and make it into pizza. It'll still work. So.
I feel like the cat would pop the balloon before you can get anywhere.
Yeah,
It might.
I just scratch the balloon until it pops.
So what's holding them together?
The rabbit?
All right. So how would I explain this? I'm going to give you a hint. As I rub these together, one of these two, either the rabbit or the balloon, has a strong affinity for the outermost part of the atoms. And one of these, either the rabbit or the balloon, is taking the outermost part of the atoms. What's the outermost thing in an atom? Electrons. So it turns out on my website there's a thing called triboelectric series, and it lists a bunch of stuff. Rabbit fur is one of them. Rubber is another one, and it lists them in terms of how much they like electrons. So the rubber likes electrons quite a bit. The rabbit fur doesn't. So as I rub this, the rabbit fur's electrons are being transferred to the balloon. And the charge of an electron is what? Positive or negative?
Negative.
Negative. So if you take the negatives off the surface of the rabbit and put those on the surface of the balloon, then the balloon becomes negative and the rabbit becomes positive. So they like one another. Now I've got this other balloon over here. There we go. And I've charged up that one. I'm going to charge this one too. I especially charged one side of it. Bring this other one over. Uh-oh, I think I went out of the picture. Have to do this way.
They repel
So,
each other.
yeah, why are they repelling?
Because negatives, like the negative charge,
Yeah, so-
like each other.
Exactly. Like charges repel and opposite charges attract. So it's attracted to me though. Does that mean I'm positive? And the wall is positive? I don't know if I could throw it up and
These
stick.
are more positive, like you have more positive.
More
charge
positive than this?
anything else.
Yeah. And we'll come back to this in a minute. I look like the Flash on my screen over there. I've got to watch this video later. See if I really look like I'm moving that fast. It's hilarious. Wonder if this will. Oh! Did you see it levitate? I'm so glad that this rabbit offered itself up to us, because this is way better than human hair. If you look at the triboelectric series, rabbit furs, human hair is not even on there. I mean, it works because we always have hair, and that's what people rub on balloons. Ooh, I'm rubbing a hair on the balloon. Anyway. So, all right.
Rabbit hair, man.
A hair. Rubbing a hair. No good if I have to explain it. So what I want to do now is go through the first 2.5 pages of these notes and get some stuff down. And then you have 2 assignments in Google Classroom. One is to answer the questions in this practice 18.1, which is some really easy dimensional analysis problems. And then 2 Mr. Pennington sort of conceptual questions, which I encourage you to think about briefly and then just cheat and look at the answers. It's fine. And then the other thing is on page 7, I think. It's balloons and static electricity simulation that you can do. It's a PhET simulation. And if you, in Google Classroom, there should be a link right to it, but you can just Google PhET simulation, balloons and static electricity. And you'll have a little bit more time to work on it than the other class, because they had to just sit here and watch me flail around with technology. So I'm just going to be working up here, which isn't ideal, but in some ways it's more fun for me. I get tired of sitting there and looking at that screen. All right, number 1, all the macroscopic forces that we experience directly, such as the sensations of touch and the tension in a rope, are due to the, this is number 1, electromagnetic force. Does anybody ever watch Vsauce videos?
Of course.
So there's a Vsauce video that I put a link on my webpage to, called Why You Can't Touch Anything. Have you ever seen that one?
Oh yeah, like you're never actually fully touching anything. It's like there's always like the most minuscule amount of space between every object.
Right.
Nothing ever
And
touches
so
anything.
why, it feels like I'm touching here. It says the forces we experience directly, the sensations of touch, the tension in a rope, the pieces of each little segment of the rope is not touching the next segment. And my hands are not actually touching. We think of touch as being 2 bits of matter totally adjacent to one another. But why is there space between my fingers even now?
Electromagnetic force.
Yeah, and like the balloons, the outermost part of my atoms are electrons. Electrons don't like one another, and if I could push past that, then there are all kinds of other forces chemists could talk about. But generally, whenever you feel a push, yeah, the wall is pushing on me, but what it's really doing is it's charges at the edge, they're repelling my charges, so we never really touch. Even though it feels cold and all, and heat's conducted to me, it's not real touching. So Mr. Pennington's just making the point that what we think of as all these forces that are pushing and pulling, they couldn't really happen without this. This is the means by which we push or pull on one another. There's no real physical connection other than that. The rest of that paragraph I think I can just skip. The two types of charges, this is very straightforward. So straightforward you probably wouldn't even guess it, but what do you think? Negative and positive. Plus and minus. Two types of charges. And we've already been over this. Like charges do one thing, unlike charges do another thing. So like charges repel, and unlike charges attract. By the way, people at home, if I get in the way, you can't see anything, just speak up. I can't hear you as well today because I don't have you routed through the speaker. So in atoms, this is a really important one. This is going to come up quite a bit. In atoms, blank carry negative charge and blank carry, actually this isn't the super important part. It's the sort of important part. So, and blank carry positive. What carries a negative charge in atoms? Electrons. And the other one is protons. Okay. Now the SI unit. SI stands for System International, which is just the fancy way of saying the metric system. The metric unit for charge is I used to say Coulomb, and then I convinced myself for years it was Coulomb, and now I'm back to Coulomb. People pronounce it differently, but it's a big letter C, and it stands for a Coulomb, and it's a pretty big unit of charge. In this example, it says the charge on one electron. So Q, little q, that's the symbol we'll use for charges. And E just means this is the charge of an electron. The charge of an electron is 1.6 times 10 to the negative 19th coulombs. So either a coulomb's really big or the charge of an electron's really small, and really both are the case. And I'm not sure why Mr. Pennington puts it in here, but this is just the reciprocal. If one electron charge equals this many coulombs, then 1 coulomb of charge is equal to the reciprocal of that, 1 over that, which is 6.25 times 10 to the 18th electron. Or I guess I should write QE. QE. All right. Can I erase this? Start over at the top? All right. So whenever a charged particle, when materials are rubbed together, charges can be separated, which is what I was doing. I was sending charges from the rabbit to the balloon in that case. Charges can be separated, particularly if one material has a greater blank than another. So what he's looking for here is affinity for electrons. Now you don't have to write this down, but if you ever want to look this up, if you ever want to figure out, if I rub two things together, which one's going to become positive, which becomes negative, just Google triboelectric series. And people have actually gotten paid to rub a whole bunch of things together and keep track of how charged they get. And they've made a list. So It's actually a useful thing if you want to build a Van de Graaff generator, for example. You want to, in some cases, have this pulley at the bottom of a Van de Graaff generator and another wheel at the top of the Van de Graaff generator, and you want electrons to leap off of the wheel down here and then onto the wheel up there, or vice versa. You need to make sure that you've got the things from the right part of the triboelectric series. And I guess in some cases where you don't want things to be charged, you wouldn't want things that have either a strong or weak affinity, because you don't want to for example, set your car on fire at the gas station. Yeah?
What is a Van der Graaf generator?
A Van de Graaff generator, it's that thing in the back. And for people who are at home, it's the thing with the big sphere on top.
Oh, yeah.
And it's got a
Something
belt like this, and it rotates. And this is a real big simplification, but it's a machine that rubs rabbit fur on balloons, kind of. You know, it's doing some rubbing down here, it's doing some rubbing up there, and what it's doing is it's basically taking a bunch of electrons in one case and offloading them out here, and then the electrons spread all around the surface of this. And it becomes really charged up, and then if you touch it, they jump over to you and it goes. So we'll play with the Van de Graaff generator. But in order for this to work, if you want electrons to leap onto this in the first place and then leap off up there, then these two parts need to have different kinds of affinities. This part needs to not like electrons, and this part needs to like electrons. And another thing that I was going to show you today, if you have some time, go to my website and click on the gas station gasoline fire. There's a woman, it looks like she's up at Maplefield. She gets out of her car and sort of rubs along on the seat, and then she gets her, like, the gas pump going, and then she gets back in and sort of slides across her seat again, and then she gets out and slides out, and then she goes over and grabs the pump handle, and the gas starts flaming up because she's been rubbing her wool sweater on the seat over and over, charging herself up.
Does that happen?
Yeah, how many of you have been shocked getting out of your car in the winter?
Oh,
I get that all the time. I get out, and the first thing I'll do is I'll just touch my elbow to the side of the car, because I find it less painful through my elbow somehow. It's my preferred way to be shocked if I'm going to be shocked. Where was I? Number 7, the law of conservation of charge. So we've been over a lot of laws of conservation, and I'll write part of it. I bet you can tell me the rest. The net charge of a closed system does what? If I have a system that's made up of I'm going to get a fresh balloon out. A fresh balloon and a rabbit fur. And this is my system. So, no matter what I do to this, like right now, this is the system, the rabbit fur and the balloon, and now I've rubbed it, and this is still the system of the rabbit fur and the balloon. What's happened to the total amount of charge here?
Zero.
It hasn't changed. Now, all that's happened is, yeah, maybe some of the negatives have gone to there, and some of the positives, well, no positives have moved at all, which is an important point. The electrons have gone to this balloon. Now this is positive and this is negative, but there aren't any more charges than there were to begin with. I might have started out with a total negative system. If I'd started out with that balloon I've already charged over there, and I had a negative system, and then I did some rubbing, and I made the balloon even more negative, it still wouldn't change the charge of the whole system. So charges aren't created or destroyed. It's basically this. So the net charge of a closed system is constant, remains constant. Number 8, this isn't a super important thing, but this is just an example of the law of conservation of charge. if you've heard of a particle accelerator, there's some really big tracks, miles long, where they just send these particles really high speeds, and they crash into one another. And when they do that, they get all kinds of new particles that are created. But it says here, whenever a charged particle is created, such as in collisions and particle accelerators, another having an opposite charge is always created along with it, so that the total charge created is 0. So because of the law of conservation of charge, you can't just create a positively charged particle without also creating a negatively charged particle in a closed system. You could bring in from outside the system some other charges, but then it wouldn't be a closed system. Number 9, this is just relating this to stuff we've already done. What other kinds of conservation laws have we done, other than, in addition to charge? What's that?
Matter.
Yeah, that's a chemistry thing. But you can put that, because we didn't do that in physics. But conservation of matter, what have we used in physics? Momentum and energy. And I'll give you the third one, which I think is kind of cheating. So there's momentum, there's energy.
Angular momentum?
Angular momentum, yes.
That's totally true.
I know, it's still momentum, right? Mr. Pennington thinks it's 2 different things. So I'll list it. All right, enough for that page. Conductors and insulators. Number 1 says blank allow electrons to easily move through them. List some examples. So is that a conductor or an insulator that allows electrons to move easily through it? Conductor. So number 1 is conductor. And so if you, silver, yeah, silver is an excellent conductor. Not just electricity, but heat too. Feels really cold. And when it's cold, feels really hot when it's hot. So conductors allow electrons to move through them, and I'm just going to say metals. But some metals more than others. Silver, if we had silver wiring in this building, that'd be great. It'd be really expensive. Sand? No, not very good. So sand, I would almost put with glass. Glass is made of sand mostly, and it's a pretty good insulator actually. So just about all metals are. What else do you have to worry about electrical shocks with? What's that? Water, yeah. So you're not supposed to use your hair dryer in the bathtub or toaster in the bathtub or anything like that. So, and in particular, salty water. One thing that I got into a few years ago, I wanted to remove some rust with electrolysis. So I put an electrode into one side of a bucket, and then it was using a car charger on the other side of a bucket, and then put this rusty thing in there. But you couldn't just use plain water because it didn't have ions and didn't really conduct electricity. So salty water or something with a lot of ions in it. Pure deionized water doesn't actually conduct very well. So number 2 then, the things that do not allow electrons to move through them, those are insulators. And so generally, conductors and insulators that conduct and insulate with regard to electricity also conduct and insulate with regard to heat, but there's not always a perfect correlation. If you wanted to have a jacket that would keep you warm, you'd want an insulator so it doesn't let heat out. If you tried to shock yourself with that jacket, like used it to wire some lights in your house, it probably wouldn't work well because things that don't conduct heat also don't conduct electricity. What's the first thing people think of when they think of insulators? Like, what's rubber? Yeah, rubber's a really good one. What's that?
Rabbit fur?
Rubber? Maybe rabbit fur.
Rabbit fur, yeah.
I don't know, styrofoam. I'm going to list the ones that are here, and you can look that up. So there's glass. I was telling this story last class. Yeah, have you ever seen the glass and ceramics? So on power lines, they have those little insulators where the wire is actually connected to the power pole. And when I was a kid, I would go with my BB gun and I would shoot them, not because I wanted to break them, but because they made a really satisfying ting, ting when you shoot them. So that was how I knew they were some form of glass. And then plastic is actually pretty good. And I would guess styrofoam would probably be good too.
I think styrofoam. Wait.
Feathers, you know, just this.
Wait, is styrofoam a plastic?
Didn't you say foam earlier?
Styrofoam.
I thought you said foam or styrofoam.
I just said styrofoam.
Yeah,
Like-
probably an insulator. Riam, do you have a question?
Yes, is aluminum an insulator?
Conductor. Aluminum's a metal. So
Yeah.
if you let's say you're wiring something. I have a barn that I wanted to get electricity out to, and if you go to Home Depot and you want to get some wire to wire your barn, there are two kinds of wires you might end up getting there. There's copper, and then there's aluminum. And the aluminum is not very good, but if you need a really, really big wire, it can be cheaper. So in some cases, like the power lines that you see, I'm pretty sure most of those are aluminum. Because copper is super expensive for miles and miles of it. And in fact, people will break into houses that are, nobody's living in, and they'll rip the walls out to get the copper plumbing, and sometimes they get the wiring too, to get the copper. All right, number 3. This is the one that, remember I was saying this is super important. This is the second half of that. Protons can or cannot flow through solid conductors. Did somebody say it?
Can't.
Cannot. Protons cannot. So in the atom, and in metals even, in this metal, for example, on the board right here, the protons are stuck there. If I hook up a big car battery and I connect it here and I connect it there, electrons can flow from here to here or from here to here. They can move through the metal from atom to atom. But the protons, they're stuck there. They can't go anywhere without it changing the whole type of atom that's there. And I added the word in solid. Does your sheet say protons cannot flow through solid conductors? Okay. Because they really can if you have salty water or water with a bunch of positive and negative ions, then those little bits of the water, they can flow from one side to the other. Okay, number 4. I'm going to deviate from the way this is laid out on your sheet. So there are these two different kinds of diagrams, and I'm going to redraw them up here, but I'm going to draw them in a more realistic way, which is what number 5 asks for. So let me give you the answer to 4 first. The two figures below are examples of induction. 4 is induction. And it doesn't really explain this anywhere, so what induction is giving, or I'll just say charging an object. Charging an object with another charged object without contact. And there is some contact in the diagrams, but the contact I'm talking about is, let's say I want to use this to charge something. I go in and I bring it near some other thing, but I don't actually touch it with the thing that I'm using to charge. So the first example I'm going to do is in the top right. There are 2 examples that go A, B, C, and D. And there's something wrong with all of these, and I'm going to do it right. So in figure A in the top right, we've got a couple of, Teaching middle school for so many years, I get the shakes drawing 2 spheres so close together. But I can do it now. So we've got these spheres touching one another, and if you look on your paper, figure A doesn't have any pluses or minuses in it, and all of a sudden in figure B, there are a bunch of minuses on the left side and positives on the right. According to the law of conservation of charge, that can't happen. So what I'm going to do, I'm going to draw them like this, because this kind of makes more sense to me. But it's really the same thing, because what I'm drawing is two neutral objects touching one another. This one's got 4 negative charges and 4 positive charges. You could think of those as 4 electrons, 4 protons, whatever. This one's got 4 negatives, 4 positives. So the net charge of this is 0, that's 0, the whole thing is 0. So then they have this wand that they bring in next to it. And I'm going to draw this again, but with this thing, which is, this would be like the rabbit. Maybe this is made of rabbit fur somehow, and they've been rubbing this thing on a balloon, and they've got it all charged up positively. So which of the particles is gonna move? Positives or negatives? The negatives. The positive, the protons can't move. They can't move from where they are. So they're stuck there. And where are the negatives going to go if I bring in this positive wand over here? They're all going to go to the left. And the ones over here, can they get into this one? Yeah, because it's touching. So protons, I need to draw just like I did before, more or less. But now all 8 electrons should be somewhere over here. They're going to be attracted to this. So the picture that they have, they're just simplifying this. They're saying in the beginning, there's the charges, this whole thing's neutral. We've got even distribution of charges. And then when we bring this positive thing in here, that causes the near side to become negative and the far side to become positive. Just like what I have in the diagram, except this is more realistic, because it's not like the protons can all go over here and the electrons can all go over there. But this side has become strongly positive and this side has become strongly negative. Does that make sense? So then the next step, which I'm not going to, I guess I will draw this. The next step is they could do these 2 things at once, although what they did is first they moved this over. Actually, they really do need to do it in this order. They kept the wand there. They took this sphere and moved it to the right. Then they brought the wand away. But I'm just going to draw what everything looks like afterward. Oops, sorry. I'm not touching anymore. So what should I draw for the right one? Like, let's say they separate this, they bring this away. What does the right one look like? What's its charge? Positive or negative? Positive, how many? 4. So this would have a +4 charge. Just draw it just like it was before. Now over here, it's not going to look like this. How's it going to look different? What's going to be different about this compared to what it looks like here? The electrons aren't going to like being next to one another over here. They're only over here together because this net positive charge is pulling them over. So once that strong positive charge leaves, they're going to push away from one another as strongly as they can. So I don't know, something like that. So the overall charge of this would be a -4 charge, and this would be a +4 charge. But the entire system would still have a neutral charge, so charge would be conserved. So there's that. Can I erase that? So down at the bottom, I don't really care if you drew any of that, but you might want to make yourself some notes that in reality, this is misleading. This makes it look like the protons get pushed over, which they don't. So that's one way to charge by induction. The other way is to actually introduce this concept of a ground. And, you know, actually, let's jump to it. Turn to the top of the next page, or you can just listen if you want. So This is my definition of a ground. Usually a large, nearly neutral reservoir of charge. For example, the Earth. The reason it's called the ground is because the ground serves as a ground, into which excess charge can flow from higher concentration to lower concentration. And I'm going to stop there. I'll come back to the rest of the definition in just a second. So this next situation involves the ground. So here's we just got a single sphere this time. And just for that, I guess I'll still make it a positive wand that's brought in. So here's the positive wand. And they show 3 electrons and 3 protons, or 3 negatives and 3 positives. But I'm going to do it differently. I'll just put, actually I guess I'll do 3. So I've got 3 positives and 3 negatives, but the negatives aren't going to stay there. They're going to get moved over here. I don't know exactly how they're going to do it, but they're going to go to the, oh wait, I screwed that up. Where are the negatives going to go? They're going to go over here. Yeah, they're going to be attracted this way. So, don't know exactly where they would go, but they're going to go to this side. So we've got, again, we've got a negative side and a positive side. So now, here's the ground. And I could keep going and going and going with this. Somebody takes a wire, a good conductor, and they run it from here to there. So which is more positive, the ground or the right side of the sphere?
Ground.
The right side of the sphere.
Which is more, which?
Like, what do you, net terms?
So we've got, think of these as people. We've got positive people and negative people living around here. If you think about the population density of the positive people and the negative people, it's pretty even there. They're evenly distributed. Over here, we've got a high density of negative people. Over here, wouldn't you say we've got a higher density of positive people than negative?
Yeah.
So in chemistry, did you learn about concentration gradients? So this is a high concentration of positive charge over here. This would be a high concentration of negative charge. Here, we've got it's kind of equal. It's just neutral. So if you compare the positiveness, the concentration of positive charge, where's positive charge more concentrated? In the ground or the right side of this sphere?
The right side of the sphere.
The right side of the sphere. So if this is more positive and this is less positive, and these electrons can do what they want, are they going to stay in the less positive, more negative area, or are they going to go to the more positive area? They're going to go to the more positive area. So by forming this connection here, some electrons, I'll just write E negative, they're going to go up here and they're going to like start to fill this in. Maybe I'll just draw 1 in here because it'll keep going until the concentration of electrons here is the same as there. It's not going to pump so many in here that we've got a really negative place now. But at least this will add electrons until this side of the sphere becomes neutral. It won't go beyond neutral because it's leaving a neutral place. So you have that, and then if you remove the wire, the electron is stuck there. If you remove this, what happens then? How should I fix this diagram? It doesn't look exactly right. Are these electrons going to want to stay close to one another over here? They're probably going to evenly distribute around here. I don't know exactly how they're going to do it, but they would spread out from one another and evenly distribute. So in the end, we get a more, like, this thing has become negatively charged. The wand that moved in here, it didn't actually touch it at all. And another way to do this would be, is if we had put some more charges. I feel the need for lots of charges. So here we have a negatively charged wand. What's going to move in here? Proton, the positive charges or negative charges? Which ones are going to move? Only the negatives can move, only the electrons can move. So these electrons are going to go which way? To the left or to the right? Which way? To the right. So this one, this one, this one, they're going to go over here. And we're going to have that. So now the right side of this is more negative than it is positive. And if you connect this wire to the ground, what's going to happen? Are electrons going to come out of the ground and go into here, or come out of here and go into the ground? Would you say go from the ground or to the ground? To the ground, right. Here, there a bunch of negatives all concentrated together, and they're going to move to a place where their concentration is lower. So they're going to, this pushes them to that side, but then they push away from one another, and some of them are going to go down here into the ground. Now, the rest of the definition of ground, the important thing about the ground is this. If I have a bunch of electrons that start to flow in here, and I do this, what's the charge of the ground now? Positive or negative? Negative. But by definition, something that's a good ground has so many charges that as soon as these negatives get here, they spread way out. It's like a giant ocean where you're just dribbling in little tiny drops of something. They spread out enough that the overall concentration doesn't change. So I can have a big battery, I can run a wire down to the earth, and electrons will keep coming out of that battery just until it's totally depleted. It's not like I'm going to fill up the earth, make the earth so negative that they start backing up. That it's always a big thing that can take a lot. So I don't feel like I did a great job with this second one, but if you just look at your picture on the page, what that shows is, let me just sum it up one more time. It shows a positive wand coming in, and that shows in their sort of language, the positive charge is being pushed to the right, the negative charge is being pulled to the left. Then when you connect this wire, the ground is more negative than this, so electrons go this way. In reality, positive charges don't get pushed over there. It's more like what I did. Negative charges do get moved here, but this does become more positive, giving the electrons from the ground a place to go. If that's confusing, we can revisit that later. So the top of the next page, the definition of ground, it just, the second part of it talks about it being important that the ground is a large reservoir so its concentration doesn't get changed. All right, polarization. So can somebody tell me a polar molecule? You should all know of at least one polar molecule.
Water.
Water's the polar molecule. And
Carbon dioxide.
what's that?
Carbon dioxide.
Carbon dioxide. And what makes water a polar molecule?
It's the electronegativity, isn't it?
Right, yeah, I'm looking for a simpler definition. You're explaining why, but basically it's just that the oxygen is more negative because it's got a higher electronegativity, and then the hydrogens are more positive. So the answer to number 7, what is polarization? It's just separation of charge in an object. Are they watching one of my videos in there? Sounds like me. All right, and I'm excited to do this again because I did a bad job with it last class. So number 8, there are 2 pictures. I'm going to draw them both. This is some object, and a negatively charged wand is being held next to it. This is figure B. And in that, we've got what looks like 6 molecules or atoms or whatever you want to call them. And within the atom, we've got a positive side and a negative side like this. And then in C, same thing, this negatively charged wand that's brought in here next to this object. And this whole object has positive side and a negative side. So both of these are polarized in a way. This is polarized because charge is separated, positive over here, negative over there. This is polarized on the atomic level. There's positive on this side of an atom, negative on that. Number 8 says, the diagram on the right shows polarization by negatively charged rods. A conductor is polarized in diagram blank, and an insulator is polarized in diagram blank. So one of these is a conductor, one is an insulator. Question is which is which? So raise your hand if you know which one. And it could be people from home. Which one is the conductor, which is the insulator? David?
B is a conductor and C is an insulator.
No.
No. Wait.
So C is the conductor, B is the insulator. Who can explain why or how we know that? Reese?
Because if it touched anywhere on the top one, there's no place where there's just electrons, there's no place where there's just protons, so it can't flow as easily.
Yeah, I see what you're saying there. Yes. I'm just going to put it a simpler way. One of these shows electrons or charge actually flowing through the material. Which one had charge flow from one side of the material to the other? That'd be this one.
Yeah.
And that's what you're talking about. There's no way for these charges to actually move to the edge of it like they can down here. So again, this is not how it would look in reality. In reality, we'd have something like this, you know. Maybe in the beginning, there were positive and negative charges all along the left side, and then when this negatively charged thing was brought in, it pushed these 3 negatives over to the right. So now it's like this. They make it look like in their diagrams that all the negative gets pushed to the left and all the positive, negatives get pushed to the right and the positives get pulled to the left, but protons can't actually move. But anyway, this is an insulator. These electrons in an insulator, they can't leave their atoms and flow to the other side. In a conductor, the electrons can flow all the way to the other side. And finally, if you were holding on to this rod or this rod, what would you feel? What? Resistance to what? Like, especially this one. Let's say I'm holding this negative rod now, and I'm holding it next to this with this distribution of positives and negatives.
It's going to want to attract to the positive end, so it's going to be pulling.
It's going to pull me toward it. And that's what's happening, not when that's not what's happening with the balloon and the rabbit skin. So the balloon has become negative, and the rabbit skin has become positive. So of course, those are going to attract. But what's my charge probably? I'm probably neutral, right? And yet, it sticks to me. So this is what's happening to me. I'm an insulator, and my clothes are insulating. I'm not wearing silver woven shirt. It'd be pretty cool if I had a silver woven shirt. But so let me turn around this way. As I bring this negative balloon over next to my shirt, the near sides of my shirt molecules are becoming positive because this balloon is pushing the electrons to the other sides of those molecules. So that means the closest things to this balloon in my shirt are the positive sides. So that's why it attracts. So that's why it's sticking to me. It's not that look at this. It's not that I have the opposite charge of the balloon. All right, so the answer number 9 is they attract. 9, it's say rod pulls toward the objects. Right. So as I was telling you, the first two questions on here and the practice 18.1, think about those. If you know the answer, great. If you don't know the answer, just look at Mr. Pennington's answer. Feel free to rely on those. And then all these questions right here, they're just relying on the relationship between 1 coulomb or coulomb or 1 electron being 1.6 times 10 to the negative 19 coulombs. That's all you need to know for all those problems. And then there's the PhET simulation where you rub a balloon on a sweater. That's it. Let's stop the video. People at home, you can go. Do you have any questions? Oh, I don't think it ever started recording. It's still working on my live stream. It hasn't actually started video transmission.